Yeah, so hello and welcome to the extra session for the statistical mechanics course. So my name is Parasar. I am a PhD student at ISC in physics. Yeah, so let's discuss some miscellaneous or some problems uh, uh, which are related to this course. All right, so yeah, so let's look at this first question. So you have a cylinder and it has two compartments which are separated by a freely sliding piston. Uh, so this is not fixed, so it can slide freely. And there are two Fermi gases placed in each of these compartments. Uh, so let's say this is compartment one and this is two. Uh, Now the spins of these particles are different. So both of these gases are made of fermionic particles, but so these have spin half and these have spin 3 half. So both are fermions, but with different spins. And it is also given that they have the same mass. So both containers have particles of same mass. So now let's look at what is asked in the question. Uh, so we have to find the relative density of these two gases, or the ratio of the densities of these two gases at equilibrium at two temperature limits, one at t equal to 0 and the other at t is equal to infinity. Okay, so uh, let's uh, uh, let's discuss what is the equilibrium condition. So since the piston here can slide freely, the volume is not fixed. What will be equal at the equilibrium, or the equilibrium is attained between these two systems when the pressure of both these gases becomes equal. Yeah, so since the piston can slide freely, so at equilibrium, uh, there should be no net force on the piston, and hence the pressure should be equal in both these compartments. Okay, that is the equilibrium condition. And now the question is about various temperature limits. So 1 at t equal to 0. So let's start with that. So now 1 is at t equal to 0. Uh, so we know that in this limit we have a degenerate Fermi gas for both these gases. Uh, Now we have to look at how the pressure at zero temperature, like the Fermi degeneracy pressure, that depends on the spin of the particle, basically. So since these two gases have different spins, we have to find out uh, the ratios of densities such that we have the same pressure. Okay, so uh, yeah, so it is known. I mean, we have also discussed in one of the previous sessions that you have a non-zero pressure at zero temperature for Fermi gas. This is the degeneracy pressure, and we can find this as follows. So first of all, uh, we know that for a non-interacting Fermi gas, ideal Fermi gas, at all temperatures we have this relation between pressure and energy density. So we might as well use this at T equal to 0. And here E is the total energy of the filled Fermi sea. It is the total ground state energy of the Fermi gas, which is nothing but the sum of all the energies of all the single particle states that are filled at T equal to 0. Okay, so we have to find this. Yeah, so let's start with the density of states because that's where the spin enters, and then we'll see how the pressure depends on the spin and the density. Okay, so if you have spin S, then we know we have a 2s plus 1 factor in the ground state degeneracy. 2s plus 1 factor in the density of states because like the single particle because there are simply as many more single particle states. So the single particle states are labeled by the momentum and the spin. Let's say sigma, let's say as Z, and this Z can take values from minus S to plus S. So these are 2s plus 1 number of values. So so for a given momentum value, there are 2s plus 1 single particle states. So there is this factor of 2s plus 1 in the density of states. So the density of states can be written as some constant A times 2s plus 1 times square root E. Yeah, so we have the regular quadratic dispersion in 3 dimensions. Yeah, so this is how the density of state looks. And A here is the constant involving h bar and pi, kb, and so on. Not, of course, not kb, but yeah. So but the important point is since the mass of both these, I mean the mass of both the particles that make up these different gases, the mass for both these kinds of particles that make up these different gases are equal. So this is same for both gases. Yeah, so yeah, this A involves mass of the particle and Planck's constant, and the volume of yeah. So let's also factor out the volume. Yeah, because yeah, we want to look at the density. So yeah, it might be handy to keep volume separately uh, as a separate factor. Okay, so this is how the density of state depends on the spin S, and uh, so what we now have to find is how the total energy depends on the spin S, right, and the density. So first, just start with the particle number. So this has to be equal to the density of states integrated up to the Fermi energy. So we have a certain energy up to which all the single particle energy states are filled. That is the description of that is a description of the state at T equal to 0. And then we have integrating this. So this is nothing but yeah. So this is uh, the same thing that we did before, but just we have kept the spin s uh, as it is here. So the Fermi energy is 3 by 2a whole to the 2 by 3 and importantly 1 by 2s plus 1 whole to the 2 by 3 times density raised to the power 2 by 3. Yeah, so this is how the Fermi energy depends on the density and the spin. Uh, we want the total energy, which is nothing but the sum of all the single particle energy states until the Fermi energy. Okay, so this is going to be yeah. E to the 3 by 2. So that is going to be this. Uh, yeah, that's right. Yeah, so now we can substitute for the Fermi energy there. I mean the expression for the Fermi energy we have from there, which will then give us yeah some constant factors like this. But yeah, we have this uh, factor involving the spin. This is important. So this is going to be 5 by 3, and yeah, this is also of course going to be 5 by 3. Yeah, so now uh, so this is 1 by 2s plus 1. Or let's just write this as density n by 2s plus 1 whole to the power 5 by 3. Yeah, this is uh, the whole thing. Yeah, so this is how the total energy by volume goes. And finally, we can get that the pressure is 2 by 3 times this energy density. So this also goes as n by 2s plus 1 whole to the power 5 by 3. Yeah, so now we have P1 is equal to P2 at equilibrium for both these gases. And for the first gas, it has been half. So S1 is half and S2 is 3 by 2. And that means N1 by 2 to the 5 by 3. N1 by 2 whole to the 5 by 3 is, yeah, so obviously, yeah, N1 by 2 is equal to N2 uh, by 4. So that means N2 is actually 2 times N1. Did we miss some factor here? Yeah, so there is this factor of 2s plus 1 here. Yeah, sorry, I've forgotten to include that here. So whatever we have written here, that is, I mean, whatever I have written here, that is only this term. But there is this 2s plus 1 here. So that means E by V goes as 1 by 2s plus 1 whole to the 2 by 3 times n to the 5 by 3. That's how the density of energy depends on the particle density and the spin. And so pressure also being equal to constant times energy density. This also goes as n to the 5 by 3 by 2s plus 1 whole to the power 2 by 3. And now, since P1 should be equal to P2, we have, and we have S1 is half, S2 is 3 by 2. So that means N1 to the 5 by 3 by 2 to the 2 by 3 is N2 to the 5 by 3 by 4 to the 2 by 3. Okay, all right. So now we can write it's 2 to the 2 by 3. And so that means N2 by N1 is 4 to the 1 by 5. Or yeah, N2 is 4 to the 1 by 5 times N1. Yeah, so this is how uh, I mean, this is the ratio of the densities, particle densities at zero temperature. So we have looked at how the pressure depends on the spin and the density, and since the pressures have to be equal, we got a relation between the densities. Okay, so that is at the zero temperature, and now we can discuss the case when the temperature is infinity. So in this case, uh, the Fermi gas uh, is almost like a classical ideal gas. So we know that the equation of state is PV is equal to NKBT and plus some corrections which go to zero uh, at very high temperatures. I mean, like these correction terms go to zero as the temperature tends to infinity. So at very high temperatures, the Fermi gas is almost like a classical ideal gas. Uh, so these go to zero as t goes to infinity. So this is a small z expansion. Uh, so if you remember, this z is the fugacity, and as t goes to infinity, this parameter becomes very small, and uh, these correction terms in the expansion involve higher and higher powers of z. So and they approach zero as you take t to infinity. So we have this equation of state, which is basically the same equation of state that you have in a classical ideal gas. So for this, the pressure is just the density times uh, kBT. So at equilibrium, we have P1 is equal to P2 and T1 is T2. So that means N1 is equal to N2. So at very high temperatures, the densities of both these gases uh, will become equal. Whereas at T equal to zero, at zero temperature, we saw that it is some ratio not equal to one. So the the density of the second gas will be higher. All right, so let's move on to the next problem. Yeah, so this is a problem where we will discuss this phenomena of thermionic emission uh, using whatever we have learned about Fermi gases. So this phenomena of thermionic emission is something like this. So if you take a metal and heat it, you will observe that there is an increased flux of electrons coming out of it. Uh, so you will see charged particles, like some flux of charged particles as you heat a metal. Uh, so we will model metal as a gas of non-interacting electrons. Uh, but in this potential well. So so let's say this is like the outside. Let's say here the potential is zero, but the inside of the metal is modeled as some potential well for the electrons of some depth W. So the electrons will need some energy to cross this barrier and come outside the metal. So naturally, we expect that the rate of electron emission will increase with temperature. Yeah. So I mean, so even if you have some classical particles, there is a barrier which they have to cross. Then obviously we will expect that as temperature increases, it becomes easier. It becomes more probable for the particles to cross the barrier and come outside. Uh, yeah, so that is not specific to fermions or anything like particles with fermionic statistics. But yeah, we'll see that the exact functional form of how that depends. Uh, I mean, how the rate of electrons emitted or the particle current depends on the temperature. This exact form will be altered if you consider the electrons inside metals as fermions, like you should. So the calculation which assumes that the particles are classical particles will give a different factor. But yeah, here we'll treat. I mean, uh, we will we will think of these electrons inside the metal uh, as uh, 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 as being part of a Fermi gas, and and see how to uh, calculate this current. Okay, so yeah, so let's draw it here also. Yeah, so this is, let's say, the z coordinate. Where this is a plot of the potential versus the z coordinate, and the metal looks, let's say, something like this. So this is the surface normal to z direction, and let's say this is the only surface we have for the metal. Let's say it is like infinite in the, or let's say periodic in the other directions, and we'll be measuring the particle current that is emitted from the surface, or rather the flux of the particles emitted from the surface. So let's first discuss which particles, or like what is the criteria for a particle, for a fermion, to be able to come out of the metal. Yeah. So clearly we can say that since there is this potential well W, the speed of or the velocity component of the particle in the z direction should be at least so much to overcome this barrier. So if so, it should have enough kinetic energy. So pz squared by 2m, that must be greater than the potential well W, the potential width W. So if pz is greater than square root 2mw, and also, yeah, of course, so pz has to be positive. So let's say an electron traveling in the, or let's say, yeah, let's say we have an electron that is in a state with pz negative. So that would correspond to something that is moving downwards away from the surface. But yeah, we don't want that. That will not be able to cross the surface and get emitted. Yeah, so we need pz to be positive and also greater than this. Then the electron will be emitted. Yeah, this is the condition we have. Okay, and yeah, what we have to find is the current density of electrons coming out of the metal. All right, uh, so let's take, so first just look at uh, the number of electrons emitted in time delta t. Yeah, so this is just like a classical calculation of flux. Uh, so if this is the surface, then uh, all the electrons within a slab of delta z uh, equal to uz times delta t. So uz is the speed of the or the velocity, z component of velocity. So all the particles within this slab traveling uh, yeah, so if you look at particles traveling with speed the uz, I mean whose z component of velocity is uz, then all the particles within this slab of thickness delta z will have been emitted. So we'll have to sum over all these possible values of uz, and also uh, the values of ux and uy, or let's say px, the moment of px and py. These can be anything. So all we need is that uh, Pz is greater than square root 2mw, like we discussed, and Uz is nothing but Pz by m. So now we want to find the number of electrons that are there in this slab and traveling with the speed Uz. Yeah. So let's first start with the density of states. So the allowed values of momenta are so first let's look at the allowed values of kx. I mean, since it is more familiar, uh, and px will be h bar k. So that's h by lx times nx. So the density of states in p space is uh, is volume by h cube. Yeah. So this is in the entire box. So if you have a box of volume v or a container of volume v, this is the density of states in the p space. Now, let's say you have the area of the surface is A, and what we want to calculate is the density of states for this small slab. So now that will be equal to, so the area of the slab is A and the thickness is delta Z. So this will be nothing but A by h cube times delta Z. So delta Z, as we discussed, is uz times delta t. Okay, so now we can write that the number of electrons emitted in time delta t is equal to the area by h cube times delta t times integral. Uh, so we have to integrate over all possible values of the momenta. So px can be any value, so can be py, but pz has to be greater than this quantity square root 2mw, and then we have the Fermi function, which is 1 by e to the beta into e of p bar minus mu plus 1 times uz. So we have this uz here, which is pz by m. Yeah, so let's just uh, try to look at this formula again and try to understand where this is coming from. Uh, so we looked at the density of states uh, for the particle having a certain momentum. I mean, in the momentum space, we looked at the density of states. But since we are interested only in the particles that are present in a thin slab of some width delta z, we have this uh, factor delta t. I mean, which makes sense because we are looking at the number of electrons emitted in the time interval delta t. So that is obviously proportional to delta t, and it is also proportional to the area of the surface. So if the area is more, obviously more number of electrons will be emitted. And this is where we are integrating over all possible momenta such that the particle can be emitted. So the pz can take values from the square root 2mw to infinity, and this is the number of this is the Fermi function, which tells us about how many number of electrons are there on average in a particular state. And since we are calculating the flux of particles coming out, that will be proportional to the z component velocity, like we derived here. And this pz by m is nothing but that. Yeah, so that is a quick summary of all the terms we have here. I mean, the origin of all the terms we have. Yeah, but what we are interested in is the number of electrons emitted per unit area per unit time. This is nothing but the flux or let's say the particle density. So this will be equal to 1. Uh, yeah, and also there is a factor of 2 for the density of states. Yeah, because of the spin of the electron. I mean, if you want to be uh, accurate and keep that, yeah, let's uh, let's put that factor 2 as well for the density of states coming from the spin. So this is going to be 2 by mh cube integral dpz p square, let's say px squared plus pn squared plus pz squared by 2m minus mu plus 1 times pz. Yeah, so now this integral I mean, in this integral, in this integrand, we have a cylindrical symmetry, which is expected because we have a slab. I mean, we have a surface terminated at some value of z. So the natural set of coordinates to think about is the polar cylindrical polar angle phi and the z coordinate and also the radial coordinate in the xy plane. So we can just do this integral. You know, these two integrals can be done, or first of all, uh, yeah. So these two variables, px and py, we can make a change of variable to cylindrical or let's say the polar coordinates. So then that will become, so since there is no dependence on the angle phi, we will get factor of 2 pi there, and let's call this p rho, which is square root x square plus py square. So this will be p rho square by 2m plus pz square by 2m minus mu plus m times pz. Yeah, so now we can do this integral over p rho first of all by letting this to be some variable t. Yeah, so whatever is there in the denominator is t, and we have this nice. I mean, this is this change of variable works because times. Yeah, of course. Yeah, I forgot to put in the integration measure. Yeah, so this can be written in terms of the variable t, so that's nice. So p rho d rho is nothing but by t minus 1. So we have this after making this change of variable, we have the this partial current. I'm sorry. Oh yeah, let's just call it flux. So this can be called, let's say, particle current density or flux. Okay, so now this will become Yeah, so when we make change of variables to the polar coordinates, we have an angle 2 pi, and we of course have p dp, which is nothing but this factor. Yeah, so that after making the change of variable like we discussed, this will become integral. Uh, so when p rho is 0, that will become a to the uh, beta times pz squared by 2m minus mu to infinity dt by t into t minus 1. Yeah, so now this integral can be first done. So let's do the t integral first. So that is, I think, yeah, so this is 1 by t minus 1 by t. Yeah, so this will become log 1 minus 1 by t from to infinity, which then becomes, so the upper limit will just be 0, the lower limit will be, with the minus sign. Uh, so we can then also write this as, I mean, once we take the reciprocal of whatever is there inside, that will become, let's see, did we get this right? Yeah, so, yeah, okay, let's just leave it like that. Yeah, so now we can see that, it's useful if you just can go back to this variable ez. Yeah, so then this will become 4 pi by beta h cube integral w to infinity m times dez minus log 1 minus a to the minus beta z uh, minus mu. Yeah, so now, uh, yeah, so let's look at uh, the the order of magnitude of these various quantities in a real material. So mu is that is the chemical potential, and we are at a temperature much less than the Fermi energy or the Fermi temperature. So the chemical potential is of the same order of magnitude as the Fermi energy. I mean, it is approximately equal to the Fermi energy, uh, which is maybe, let's say, 5 to 10 electron volt uh, in typical metals, or let's say 5 to 15, somewhere in this range, I think. And the potential W, this is in the range of maybe, I think, yeah, maybe this is actually somewhat even lesser. Yeah, so somewhere like yeah, like 5 to 10 electron volt, I think. Yeah, and this will be, I think, in the range of somewhere like 10 to 15 electron volt. And the temperature is much lesser than much less than both of these quantities. So what we have here is this exponential here. That is something which is very small. Yeah, so then we can just replace this log 1 minus x uh, with minus x. So then this then approximately becomes, sorry, and yeah. So after doing the integration, we'll find that this is beta square h cube uh, is equal to this. So we see that so of course W is greater than mu. So if you look at a picture of these various energy scales, so let's say this is the potential well W, and the Fermi energy is somewhere here, which is also approximately equal to mu chemical potential. So these are all filled states. I mean, there are states with these energies. All those will be filled, and so clearly W minus mu is positive. So as temperature increases, we of course see that the particle current increases the temperature exponentially like this. But there is this factor of T square. Yeah, so we see that the the particle current, the thermionic emission, uh, that uh, increases as t squared to the e to the minus pi by t. Yeah, so this is called a work function sometimes. So this potential well depth minus the Fermi energy. So the barrier on top of the Fermi energy is called work function sometimes. So we see that the particle current goes as t squared times e to the minus 5 by t, 5 by kBt. Yeah, and yeah, this has been uh, observed experimentally. Yeah, so if you treat the particles as classical particles, you will still get this exponential factor, but I think you will get some somewhat different dependence here instead of t square. Yeah, I'm not sure which what you'll actually get. But yeah, so once you start treating the particles as fermions, like uh, we see that we have this t squared times the exponential. Yeah, so this is one example where we looked at or try to understand a phenomena based on whatever we have learned. Uh, all right, and so yeah, that's all I have for today, and see you. Thanks.